welcome. This is Roni Ali from Middle East Technical University, North Cyprus campus. The topic of my presentation today is machine learning developed algorithms for well test analysis in reservoir depleted by horizontal wells. The outline for the presentation goes as follows. First, I will talk about machine learning in general in oil and gas industry, and more specifically in well test analysis. Then I will talk about the simulated pressure distribution that we have obtained for vertical wells. And then I will also talk about the machine learning model that we will use in our case. Also, we will be assuming some parameters. I will also discuss those parameters. Moving on, I will be talking about the model behavior, and then I will end with a conclusion and my future plans. Machine learning isn't a new concept. It has been used for around 20 years. But in the recent years, it gained a lot of popularity, and oil and gas industry is no exception from that. We started using machine learning in oil and gas industry to be able to save more time and save more money, decrease the costs of our operations. If we compare that to the conventional methods that we use in well test analysis, we will see that machine learning will be able to save us a lot of time, and it will be able to decrease a lot of our costs. Instead of going to the operations and actually conducting the operations in the field, we will be conducting everything through computers and simulated data. The first challenge that we faced was to actually have some data, and since we didn't have any real data, pressure data versus time, so we decided that we will simulate some data using the model shown under the figures. This model was taken from Salama Rabawi's paper, and in the left figure we can see that our assumption is our reservoir is a rectangular reservoir, and we have a couple of wells. 2xe and 2ey are representing the width and length of our reservoir, and h is the thickness of our reservoir. In the model that we see here, we have one assumption that we took, that we have fully penetrated well, thus the last sector or the last section of the model is assumed to be 1. In this slide we can see the rock and fluid properties that we assumed, in addition to some of the physical properties of the reservoir and the amount of wells that is available in our field. Generally speaking, the pressure behavior versus time in well test analysis is of a nonlinear nature. Thus, we have decided that we will go with a nonlinear regression method to be able to train and obtain our data. So in the equation that's seen, P measured here is the simulated data that we have obtained from the model discussed in the previous slides, and the predicted will be the predicted pressure values that we will obtain from the machine learning model. 3 parameters are very important for us here: alpha, beta, and lambda. I will also discuss how we obtain these parameters using 2 different methods. To obtain alpha, lambda, and beta, two methods have been decided to be used. The first method is the iterative method, which is basically a trial and error method. We will be entering some values and we will obtain alpha, lambda, and beta depending on a function. Also, we will be using optimize minimize function that is available in Python as a library. It's a very powerful tool that will be able to enable us to minimize the error amount that we have in our predicted values. So as we can see from the model that we are using to be able to simulate our data, the functions, like the model is a function of dimensionless time. So we started by simulating a dimensionless time on a logarithmic scale, as shown on the figure on bottom left of the slide. After obtaining the dimensionless time, we also obtained the dimensionless pressure that is simulated. Then we switched the dimensionless time and dimensionless pressure into real T, and real change in pressure. Using those values, we will be able to obtain also alpha, lambda, and beta. The first method that was used to be able to obtain alpha, lambda, and beta was optimize and minimize function that is available in Python from SciPy library. We gave the code at the beginning 3 initial guesses for the values of alpha, lambda, and beta, and then the code did several amount of iterations to be able to decrease the error amount between alpha, lambda, and beta that we gave, that we predicted, and that was simulated. So we went with the initial guesses of 1.5, 0.6, 0.7 respectively, and the values that we obtained from this function as shown are shown on the figure in the figure on the right. There are some errors since the values are not in the expected range, but further adjustment will be done to be able to get rid of these errors. The second method that we'll be using is a trial and error method that was taken from a paper from SPE journal. We will be assuming the value of lambda, and depending on the value of lambda that we assume, we will be obtaining beta and alpha values. Also, we have some errors here in this method. The error that is occurring here is because of the simulated pressure data. Since the model that we are using to simulate the data is only working for the it's only working for the transient state flow regime, we will need to separate the flow regimes that we already have simulated to be able to take into account only the transient flow regime. Further adjustments shall be done to be able to also take into account the pseudo-steady state and pseudo-steady state flow regime states. These are several plots that we obtained after both optimize and minimize method, and even the trial and error method. We got identical plots for both scenarios, but the values were varying a bit. The project future plans are consisted of 3 parts. First, we will increase the accuracy of our simulated data by being able to separate the transient flow regime from the other flow regimes that we have in our simulated data. Then after we increase the accuracy, we will be testing the data that we obtained from our simulated model to our machine learning model, and then on actual field data. After testing it on actual field data for the transient flow regime and vertical wells, we will modify our model to be able to take into account also the pseudo steady state flow regime and the steady state flow regime, in addition to different type of wells, including vertical and horizontal wells. In conclusion, we have simulated some data using a model that was taken from Salam al-Rabawi's paper. In addition, we will be using, as I mentioned previously, the nonlinear regression model for machine learning and the least square methods. And then we will also look more for more ways to be able to obtain the parameters alpha, lambda, and beta. Thank you for listening to me, and this is the reference list, and I will be glad to answer any questions.